Coming to a deep dialogue on nuclear energy, and it's going to be presented by Paul Reisberg, who's a member of the Elders Climate Action Research Group, and I'm Amy Meltzer. I'm a member of the group too. Before we begin, Paul's going to present in 4 sections, and we'll have some time for questions in between each section, and then more time for discussion at the end of the presentation. And you can put short questions in the chat, which I'll read to Paul during the break. If you'd rather speak up yourself, you can just write stack in the chat, and then I can call on you. And just in the interest of time, if you could keep your comments short during the presentation, and just we'll have more time for discussion following the presentation. And as a reminder, if you could put yourself on mute, unless it's your turn to speak, that'll help us focus. And here's Paul.
Okay, thank you. Let me
I just want to remind folks I've started recording. So if anybody has doesn't want to be seen or doesn't want to be recorded, you should be aware of that.
Okay, thank you. Thank you all for coming. So really the goal today is to figure out how does nuclear energy fit in to the overall approach to dealing with our climate emergency. And I thought I'd just start off with this figure that shows it's already having a really big role. This is electrical generation in the United States. And as you can see, 20% of our electrical generation is nuclear. It's the biggest part of our carbon-free energy, and it's about triple what we get from both wind and solar together. I guess I want to say right at the onset, what's the role going to be in Massachusetts? What's the role going to be in the United States? And there's also what the role is going to be in the world. And so maybe in the back of your mind, you want to think of all of those. At our last chapter meeting, Senator Barrett spoke to us. And for those who don't know who he is, he's among the leaders and perhaps the leading climate advocate in the State House. He's introduced many bills, and he's also the chair of the Telecommunications, Utilities, and Energy Committee, so has a very influential role. And when he spoke to us, he said that he had been anti-nuclear at one point, but that he's had a conversion. And basically he said it's because the climate goals are going to be incredibly hard, and there are going to be tough choices ahead to use every clean energy source we can get, and that we just can't afford to be purists. And that his experience is that when we shut Pilgrim down, it set us back a year. Well, it turns out it actually was worse than that, because we lost half our clean energy when Pilgrim got shut down, and we have not yet recovered from that. Anyway, looking ahead, he thought we have to make sure we don't prematurely shut down Seabrook and Millbrook, and then we have to be open to the new technologies such as small modular reactors. So those are points we'll be talking on, and I thought it was a good intro that he gave us. We all know it's very controversial, and there's a lot of black and white thinking on it. I just put a few quotes here. James Hansen, one of the leading climatologists, it's our only hope. On the other hand, there's Greenpeace saying has no place. James Lovelock of Gaia fame, it's only nuclear power can do it. And Jacobson, the Stanford professor, every dollar we spend on nuclear, we're wasting because we should be spending it on renewables. So there's a clear divide, and I'm hoping to bring some nuance to the discussion, that it's not necessarily one extreme or the other, but at least that we all come out of this better informed and able to see it in a different light. So I thought I'd just start out and tell you who I am. PhD in biochemistry, and I did my postdoc at the Department of Energy's Lawrence Berkeley lab, which at one time was known as the Lawrence Radiation Lab, and it's where Oppenheimer was from when he put together the Manhattan Project. Following that, actually, I was a paid employee for the nuclear freeze movement. So I've been on various sides of the nuclear issue. The nuclear freeze movement, if you don't know, was anti-nuclear weapons. And the last 25 years before I retired, worked in the Wellesley College Chemistry Department. And I would get myself involved in the more controversial courses such as drugs and the science of sexual differences and things like that. And I would always try to take, these are issues that similarly there were big divides, and I always try to take a more nuanced view. So today's agenda, first I want to just get us some context, and I'll talk a little bit about radiation, and then give some reasons why we even want to consider nuclear at all and how it fits into our energy portfolio. It has some advantages. And then I'll take a break after that. And
It is.
we'll look at the
Oh, I'm hearing me.
we'll look at the dangerous side. So first the positives and then the negatives. And then we'll see, does advanced nuclear address the different concerns? And then lastly, where we are going forward. And as Amy said, we'll have breaks for questions after each section. So to begin, like I said, I want to give some context just about radiation. And it's, for historical reasons, is an exotic language talking about alphas and betas and gammas. But the reality is, these are things we encounter every day in life. Alpha is just helium atoms, beta is just electrons, gamma is just light, just photons. And it's less exotic and less scary, maybe, if you think of it that way. I have a little demo here. So let me stop the screen share. And if you can bring the focus to me. I brought with me a little Geiger counter. You could maybe hear the clicking. That's just background radiation. I mean, people are radioactive, buildings are radioactive, the air is radioactive. It's everywhere, it's around us. I brought in a sample. I have a piece of polonium here. A lot more than background. One thing I wanted to show you is that this is emitting alphas, helium atoms. You don't have to move it too far away, right? So there's a strong distance dependence. So that's one thing you should know about radiation. If you just get far away from it, it's good. The other thing is it's very easily blocked. Piece of paper. That's all it takes to block alphas. Betas takes aluminum foil. Gammas is where you're starting to use the lead. And like I said, it's everywhere, right? You can hear the background. I brought in a meal here. We can get that. See what. That sounds terrifying, right? Any food in peace. Okay, well, actually, each of those are radioactive, and particularly the banana, but I'm actually playing with you because what's really radioactive there
Are the plates. It's the
plates.
Fiesta orange plates.
Fiestaware, yes. And why are they so nice and orange? Uranium.
They had a uranium glaze on them.
Uranium glaze.
They
right.
still have it.
They still have it, right? So anyway, another, just an example. It's around us everywhere. So let me back to sharing. There I am. So here we are. Yeah, so anyway, it's everywhere. And you can shield yourself and you can protect yourself with distance. And the other thing about radioactivity is it decreases with time. So if it's just things like helium and electrons and light, I mean, what's the big deal? Well, at high enough energy, it can damage DNA. And the same thing is with UV radiation. UV damages the DNA. In fact, there's no avoiding it. On a typical day, if you just took one of your cells, has about 30,000 genes. Each of those genes gets damaged 1,000 times, thousands of times. And the reason that's okay is we have all these sophisticated repair mechanisms that are undoing that damage and fixing us. So normally everything's okay. But if you've ever overloaded our system and you've gone and gotten a sunburn, I mean, that's an example of what happens. So the problems are if you overwhelm the repair mechanisms. And it's the same with radioactivity as it is with UV light. You'll get a burn, you get more, you'll get things like moles, you get more, you'll get tumors, you get more, you'll end up with cancer. So it's deadly, but only in doses that are high enough to overcome our repair mechanisms.
Paul,
Yes.
we're at 10 minutes.
Okay, thank you. So where's this radiation all coming from? Well, 84% of it is just naturally and radon gas coming up. There's some from our food, there's some from cosmic rays. Buildings give off radiation. We get a lot of exposure from medical procedures, dental x-rays, CAT scans, things like that. If you add together all the things that people are concerned about, all our nuclear testing, nuclear accidents like Chernobyl and Fukushima, and you add those entirely together, you just end up with 0.3%. So I want to talk a moment about dosing, because like I said, it's the dose is what's making it dangerous. And it's like drugs in that respect, right? So this is a log scale, so it's factors of 10 for each demarcation. The heights don't mean anything. And it says sieverts, which is a measure of lethality, I guess. So around 1 sievert is where radiation is becoming significantly dangerous, and about 5% of people will be can be expected to die. At around 10 is considered a lethal dose. It's 50%, and as you go higher and higher, it becomes worse. The fireworkers at Chernobyl got in around 80 sieverts. They're in this range, and it was a fatal dose, and they died. If we look at the responders to the Fukushima accident, they were a little under 1, and there was only 1 death, and so that fit in also. As you get down to 0.1, we're getting to now where the body is able to do repairs generally, and where the radiation dose is about what one would get 1 year on the International Space Station. And the effects on longevity is, I put in here what the effects of living in Boston because of PM 2.5. So we're in that range. People that live just outside, or people that were just outside the Fukushima plant, that's the dose they got. You go down another order of magnitude, so again, factors of 10, another factor 10, you get to what you get with a CT scan. The average background, so that's what we were just measuring. I have self-dose where people are radioactive. So we have radioactive potassium in us. You give someone a hug, you're giving them radioactivity. We give ourselves radioactivity, so that's there. Coal plants give off more radioactivity than nuclear plants, about by another order of magnitude. So that's there. People that live during the accident, we spent 2 weeks in the town of Fukushima. That's the dose you got. And lastly, I have what you would get from a nuclear power plant. Yeah, so I guess that concludes the first part. And we can take some questions from here.
So Paul, you just got a question related to this slide. What is PM 2.5?
Oh, those are small particles that actually, I'm trying to figure out how to get. Those are small particles, usually from like diesel emission, things like that. Actually, I think just even roads might put up some. So small particles and air pollution causes lung damage. Boston actually has very good air, but that is one of the things we do have is, and we're actually right at the safe level. So
Those are the big killer from coal.
yeah, 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 yeah. We'll see in a moment that nuclear is not the killer; it's coal, and it's those small particles. Yep. Any other questions, or if
That's-
not, I can go
Those are
on.
the only questions in the chat.
Okay, I'm happy to go on because I think there'll be things uh, we'll be wanting to ask questions about.
Remind everybody to mute yourselves, just so we don't get background noise. Thanks.
Right. Make sure I share the right thing here. Yeah. So first I want to just look at some arguments that would suggest why we even want to consider nuclear. And I just want people that have, the different reasons for why we shouldn't even look at it to just save that for later. And right now, just keep an open mind and we'll just view it positively. And the case for nuclear involves several things. As I mentioned already, it's a significant part of our present clean energy. So it's already doing a good job helping us in that regard. In the past, we're able to really ramp it up quickly to replace fossil fuels. And so in theory, that could happen again. We're going to need massive amounts of clean, consistent, often referred to as dispatchable power, to replace coal and gas to make electricity. So not only do we need to replace their role in making electricity now, our electrical needs are going to be 50%, 100%, 200% higher than they are as we start electrifying everything. So that electrical generation has to come from somewhere, and wind and solar will have their role, but we'll see that nuclear can work in a partnership with wind and solar. Another of its advantages is it has a very small footprint and flexible siting. So I'll get into that. And then lastly, there are these new technologies referred to as Gen 4 advanced nuclear. And hopefully those will address the concerns that people continue to have. So anyway, my first point was that we're already using a lot of nuclear. It's already a big part of our clean energy portfolio. And I'll say carbon-free clean energy interchangeably. So 10% of the world's electrical generation, 30% of it's carbon-free. And this shows various countries and their use of nuclear. But one thing I want you to see is how rapidly it all ramped up. So as a response to the energy crisis in the 70s, many countries decided to just go nuclear. And from 75 to 85, there was a gigantic adoption of it. And in theory, we could do that again. Specifically, this is looking at France. And this is France actually was a little bit later on that. So it was like 84 to 94, but it shows the yellow shows the nuclear generation. And you can see it just took basically a decade for France to very largely replace its fossil fuels. And it's not just France. Many other countries have done this. So this graph shows it takes a decade of the peak scale up of different energies. And we see Sweden was the biggest example in terms of scaling up nuclear very largely and very quickly, then France and 9 other countries before we get to how quickly countries have been able to scale up the renewables, wind and solar. And so historically, it's been nuclear, not the renewables that countries have been able to largely replace fossil fuels with. And so this data goes to 2014. I looked up more recent data, and the more recent increases in solar and wind are comparable to what's shown here. So on the order of 80 to 150 kilowatts per capita. So it's still, as much as we're hoping for wind and solar, it's not happening at the speed at which in the past we've been able to do nuclear. So that's one argument. Just historically, when we've needed or there was desire to replace fossil fuels, we were able to do it with nuclear. So to address renewables for a moment, because that is often where people are saying, well, can't we just do everything with renewables? And this is from data from PJM, that's the Middle Atlantic states. And this shows wind power over the course of 2 years. And what's noticeable is just how extremely variable, but also how that variable happens on every time scale. So you can go from 1 year to another, right? Compare the winters, one summer to another, almost a factor of 2. You can compare seasons. So from summer to winter, factor of 4, 5. You can compare month by month, goes up. You can see it's changing weekly. You can see it's changing daily. And even if you take at the winter peak, you see there are days it goes to 0. And so at every time scale, there's variability from minutes, hours, days, weeks, seasons, years. And the hope to combine the renewables with batteries requires storage for each of these time periods. And the minutes and hours we can handle right now with batteries and other things like perhaps and pumped hydro. We can probably get up to days, but there really doesn't seem to be anything on the horizon that looks affordable for the longer periods of time. So if we look at energy generation or electrical energy generation, it involves 3 different classes. So there are the renewables, and the fact that the renewable is their big strength, and the costs have been coming down. And so that's an advantage. But as I just showed you, you can't depend on them. They may not be there. They come and go, and the amount varies. And so the next category is what's known as flexible baseload. And this is energy that can be just turned on when you need it. It's there, you can depend on it. You can vary it, you can tune it up, you can tune it down, and it's consistent. So there's several terms for this: firm energy, dispatchable energy, baseload energy. So, but the point is you can just turn it on and you can modulate it, tune it up and down. It's steady and dependable. And that is the, baseload is used for a reason. It's the base of our energy. And the third is the fast burst, and that's to make up for the way the load changes and makes up for the variations in renewable. And that is mostly peaker plants, although batteries and other things can make it up. But the more we're dependent on, or the more we use renewables, it's been lately the experience that the more fast burst, and most of the fast burst has been gas peakers. So let me show you an actual example of what a mixed portfolio looks like. So this is looking at Germany at the peak of the summer when the highest solar. So the yellow is the solar. This bluish gray is wind. These shades of brown and orange are the different fossil fuels. The red is nuclear, and then we have biomass and hydro. So anyway, you can see the variables, and then you can see the base load, the ones that are consistently there. And if we want to be replacing the fossils, which are used as base load, you can see what'll match up well, what makes sense to replace them is going to be nuclear, hydro, perhaps biomass. Biomass has its problems, but it fits that role. Hydro fits that role. It has issues too, and there's actually just not enough hydro to do it. So this is probably the second main argument. The first, I thought, is that the rapid adaptation that you can do with nuclear, but the second is this replacing the role of the fossil fuels as a dispatchable firm energy. We can
Oh,
look at two countries. Yep.
well, we're at about 10.
Okay. Thank you. We can look at two countries. France and Germany, they both aggressively decided to pursue carbon-free electricity. France took the approach with nuclear, Germany with solar and wind, and in fact has been decreasing its reliance on nuclear. And the effects have been that France has become largely carbon-free and twice the clean energy of Germany, and it's done it at half the cost. And studies have shown that if Germany had instead made the investment in nuclear that it made in solar and wind, it would also be 100% carbon-free now. Another advantage, I said, is small footprint. So this is how much land use does it take to make a given amount of electricity. And this is where environmental justice issues can come in. Not surprisingly, hydro takes a lot. This includes not just, the lake, but also transmission, and that's true for wind and solar. Nuclear is basically the same size as a coal plant or a natural gas plant. And so if we're going to be replacing coal and natural gas, it has the advantage that you can do a one-to-one. You could just take a coal plant and put a nuclear plant there. It has another advantage in terms of siting. You can put a nuclear plant anywhere as long as there's some access to water. It's not, solar, you have to put where the sun is, wind, where the wind is, hydro, where you can. So this flexible siting and this smaller footprint is another advantage for nuclear. And one way to visualize this was in the New York Times last week. This shows the wind and solar footprint presently of wind and solar. And if we step ahead to what we are going to need in 2050, we see that. So today, where we need to be, and I'll just let that speak for itself. And the last point in nuclear's favor, and it's probably surprising to at least some people, is that it actually has the best safety record. Yeah, whoa. This is a study done by The Lancet. They looked at energy and health, and they did a whole series on it, and they came up with a statistic they called a death print. How many deaths does it take to make a given amount of electricity? And so the given amount is 1 trillion kilowatt hours. And if you look at the inset, it's not surprising that coal is the big killer, and that's pollution and various means. So it's 100,000 deaths, and an order of magnitude less for natural gas. And actually, it turns out an order of magnitude less for hydro. And then I blew up the hydro. So hydro is still, there's still deaths, dams break, things like that. So over 1,000. Solar, half that, better than half that. Wind, even less. But nuclear, the smallest, and that's really surprises people. And one reason is, a lot of deaths come from mining. Nuclear having about 1 million-fold higher energy density. There's not much mining. There's not much transportation. Another place where deaths can occur. Because people are so very worried about nuclear, there's excessive safety involved in it. And you put those all together, it has the best safety record. And James Hansen, after Fukushima, was worried that people would panic about the use of nuclear. And so he wrote a paper, he did some calculations. And by his calculation, between over the 40 years from 71 to 2013, 2 million lives were saved by our use of nuclear energy, by replacement of coal and natural gas. And he actually extended further, and I think by 2050, he figures another 3 to 7 million lives will also be saved by nuclear. But some people say, well, okay, well, maybe day to day it's less, but how about the catastrophic accident? And so I went through and got data on the largest energy accidents, and the top 40 are all coal, oil, gas, and hydro. And some staggering numbers, hundreds of thousands here for a dam, 10,000, 2,000, 1,000, 1,000. I just want to point out, I don't think most people, the average person has not heard of the Banquo Dam, 100,000 deaths, 170,000 deaths. Most people have not heard of the Benzeshu mine, sorry, misspelling it there, in China, the Courier mine in France. I mean, these are just not things that people know, and yet staggering numbers. But if I go down to nuclear, which begins at number 42 for the largest, yeah, I mean, there have been big accidents and many people have died, but not on the scale of other energy. So historically, the fear that nuclear is going to cause gigantic numbers has not happened. Now, just these numbers may shock some people because, wait, didn't millions die at Chernobyl, or hundreds of thousands, or at least tens of thousands? Why am I saying 95? So we'll get into that in the next part. But yeah, so I'll save that for then. And I think that is where I wanted to break. Whoops.
And we have a couple questions in the chat. One of them is deaths from solar. Are they from mining?
So solar, well, it turns out the main cause of death from solar is people falling off the roof.
Yeah.
Surprising, but that working on a roof is dangerous, and a lot of solar is rooftop, and that turns out to be the main one. But then after that, it's combinations of transportation and mining are mostly, and then just random accidents whenever you're doing manufacturing, right? There's being manufacturing. The reason nuclear is so low is really just that incredibly high energy density. You don't do much mining. You build your plant, but you're not transporting a lot around. It's there and it just runs, right? Other things there's a lot more manufacturing involved.
Okay, another question, and someone posted an answer, but Bill Gates is working on a modified nuclear power plant model. Any comments?
Yes. Well, we'll actually talk about that. So there is a plant he's just started in Wyoming. Sorry, I kind of lost you guys here. So, and yeah, I'll address it for a moment. So yeah, my view is we have to be all in on, we need to try everything. The effect, sorry, I'm incompetent here, so I need to get to where I can see you guys and not lose my presentation. Oh, there you are. I don't know if people saw the New York Times had a climate issue this weekend. It's try everything, right? So that's actually where I'm at. We really, all hands on deck. This really is an emergency. In an emergency, you can't be too picky. So there are these, so Bill Gates, Terraform is the company he's involved in, and they've tried a couple things. This new plant is a liquid sodium reactor. So yeah, I'll talk about that in a moment.
So Michael Sales just posted some thoughts. Michael, do you want to say what you have here? Michael Sales?
Sure. Well, what I said in the chat here, Paul, is that I believe that we are engaged in what I call meme warfare. That powerful images are what mobilize people into impassioned action. So for example, the image of Chauvin's knee on George Floyd's neck enraged millions, or the blackouts. Images of blackouts are very deeply concerning to people. Images of Fukushima are very concerning to people. So I'm wondering, do you have any ideas, or do you have any?
Well, actually, I tried to do a few already, right? I mean, I was holding uranium in my hand, right? I was hoping to normalize it that way. I talked about alpha, beta, gamma as helium, electrons and light, right?
Well said.
So those are, I mean, to me, it's that sort of thing. It's to make it less exotic, to make it more normalized, to show that this background, to realize that people are radioactive. So that's part of it, I think, is a normalization and a less exotic.
I think that's very powerful what you just said. I really appreciate it. I'm asking, the question I'm asking is, have you seen memes that are comparable to what you just said, that turn the grizzly into Smokey the Bear as far as nuclear power is concerned?
Well, I'll tell you where to find them. on Reddit, there's a nuclear subreddit. Are you familiar with Reddit?
I have heard of Reddit.
Yeah, so if you look at Reddit, and it has its own nuclear sub, and there they do, there'll be cartoons and things like that do, I mean, that's the place to look for that.
Okay.
And I mean, I showed you the Gilbert radiation set, right?
Yes.
So it was another way I tried to do it, and I have another figure too later on. But yeah, no, I agree that is. Well, a lot of these things are just emotional.
Sorry.
Yeah, go ahead, Dave.
I agree with this point too, because I think this is the big issue. Is the memes that are out there? It's not the technology. And it's the Simpsons, and it's China syndrome, and a lot of other things that are way overblown.
Yeah, no, you're right. Simpsons has been a disaster for the nuclear movement. The three-eyed fish, right? And and 3 Mile Island happened right as China syndrome came out. Was also part of the problem. Yeah.
That's it in the chat.
Okay. Yeah, I'm okay to keep moving because I think we're getting into the part where questions will come.
Right.
If I can get back to screen shared. Yeah, so I seem to have lost it. So let me find it again. Yeah, just seem to lost the whole thing. So it's somewhere on Google.
I just want to remind everybody to mute again for the next section.
Yeah, I seem to have closed it somehow. So, figure out where it could have gone. Oh, there we are. Okay. Okay, it's not showing up as one of my choices on share screen. That's strange. Let me share, get out of share, and then if it doesn't show. Oh, is it showing for people? I don't know if you're seeing
Yeah,
Yes.
Good, Paul.
Okay. So get back into view mode.
present.
Present. Yeah, here we are. So sorry, I must have clicked something to erase it. Okay, so we're going to look at dangers and specifically look at those accidents that are so in people's minds, rightly or wrongly. And when I was making this slide, I came across this news item and it showed a power plant in Puerto Rico that series of explosions and a fire following a cyber attack that morning, and left 500,000 without electricity. I saw many articles that day, but no follow-up. And it just struck me, okay, this was in the news cycle for one day and gone, but had it been a nuclear power plant, it'd be up there and, our great grandchildren would be talking about it, right? So there's power plants and then there's power plants. So I'll talk about those accidents. I'll revisit radiation and why people have such an inflated idea of how dangerous these things were. And then an issue for a lot of people is just what we do with the waste. So I'll come to that. And in terms of terrorism, I'll save that for the Q&A, but I will point out that unlike other power plants, all nuclear plants are disconnected from the internet. There are no internet connections to any nuclear power plant. So in that regard, at least, they're much safer than, as we saw, is our gas infrastructure, and in this case, a power plant. So to give a context for the nuclear accidents, a little bit just on how nuclear reactors, most of them work. So to generate electricity, you need to spin a magnet. That's a generator. That's generally spun by a turbine, and that could be hooked up to a windmill. It could be hooked up to a hydropower plant to spin it, or you can just generate gas to spin it and generate the gas by boiling water with either coal or gas or biofuel or something. Or you can have a nuclear reactor, and the nuclear reaction heats up the water, you make gas. And so the part on the right is the same for all these. It's just how do you create the heat? And to get a chain reaction happening, you need about 3 to 5% U-235. And to make a nuclear weapon, you need about 90%. So it's impossible to have a nuclear explosion from a nuclear plant, although the two ideas are linked in people's minds, and that's one of the problems with nuclear energy. But it is not possible to have a nuclear explosion. And there is an inherent passive safety for, this would be called a light water reactor, in that water is used to make steam. Water is also used to cool the reactor, but it also has a third use. And that's that if you just have the uranium, you're still not going to get a chain reaction because the neutrons are traveling too fast. It's only slow neutrons that can be absorbed. And water acts as a moderator and it slows them down. So you need some sort of moderator. It can be control rods or it could be water. And most reactors, water is the moderator. And so what happens if there's a problem and you lose your water, right? There's a leak or something. Something happened and you've lost your cooling. If you lose the cooling, you also lose the reaction. The reaction shuts down automatically. So it's one level of passive control. Another aspect of reactors is what they call defense in depth. And because people are so worried, there's just multiple redundancies at every piece. And even just the fuel is in a pellet, the pellet's in a rod, the rod's in the cylinder's in this reactor, the reactor's all sealed. And then the entire building is put inside a containment structure, and one that you could fly a fuel-laden 747 into, and it should just stand intact. So, and as we saw at Fukushima, they can withstand major earthquakes. So anyway, so what went wrong? So this 3 Mile Island, and it was this things weren't well maintained. A coolant pump failed. They misread things. A lot of stupid things were done, and they got the reaction to slow down as it was supposed to, and everything was okay. And then they dumped some water on it, and that water leaked away. They didn't notice, and they dumped more water on it. But meanwhile, the rods had the fuel had heated up, and they poured cold water on very hot rods, and it shattered them. And there was nothing major that happened, but the reactor was destroyed. And so there were no health effects, but it was a total financial disaster. It's been cleaned up in terms of the fuel. That's all been, the core has all been removed. That's now in Idaho. Reactors have to put money, or nuclear power operators have to put money into an escrow fund in order to eventually decommission it. And so that money is what was used for the cleanup so far. And that's just run out. So the future cleanup, which is dismantling of the rest of the plant, that's just starting now. So anyway, it led to many changes in reactor design and the way, if you look at this is Jimmy Carter visiting 3 Mile Island, and you can see what the control room looked like, and they've modernized control rooms. So you see it's much more easier to see what's going on. They changed how training happens. You now have to have a nuclear engineer on site at all times. There wasn't one then. And it can be boring for a nuclear engineer to just sit there and watch nothing happen day after day. And so the way their work cycle works is they spend 1 week at the reactor watching nothing happen, and then they spend 1 week in a simulated reactor that's identical, and they make everything happen. So, you know, what if a meteor hits it? What if there's a nuclear war going on nearby? What if a plane crashes into it? What if, whatever. They imagine different scenarios each week and create these disasters, and they practice in dealing with those. Chernobyl, far more.
Yeah. Paul, we're at 7 minutes.
Okay, thank you. Chernobyl, a more serious, much more serious one, but it's unique in that it's a different design, what I showed you. It didn't use water as a moderator, so losing cooling did not shut the reaction down. Instead, it has graphite modulators, and there's no containment building. And so when it blew up, there's nothing to contain the radioactivity, and there was nothing to, in fact, it was set up, the design was such, instead of the reaction slowing down, it would speed up under the conditions that they were dealing with. But what happened, it was just incredible incompetence. They were shutting down the reactor. They decided to do some tests. They shut off all the alarms to mimic a power failure, and the reaction did stop. And the problem is the night staff wanted to keep doing the experiment, and they kept trying to ramp up the reaction. They kept removing fuel rods until they essentially removed them all. And then the reaction started up, but it was now uncontrolled. And a lot of hydrogen got generated, and there was a chemical explosion. The hydrogen reacted with the graphite. 3 people died in that chemical explosion, but it blew up the reactor. There being no containment, radioactivity spread. Firemen were brought on, as I showed you earlier. They got very high doses. 28 of them died. And people in the area, there have been an increased number of cancers, and 32 have died. Hundreds of thousands of people were evacuated. There's a 30-mile exclusion zone where reactivity is above background, but they've been shrinking it gradually as the radiation disappears. But anyway, because other reactors have containment buildings, other reactors use water moderators, so the reaction stops when you lose your water. So it's not something that can be repeated. And I guess also I should say, they have added a containment building. So they built the containment building around it. That containment building has started to weaken. And so they've now built a second containment building around that. So that's sort of the status. I'll say a bit about Fukushima. You know, the 4th largest earthquake ever on record, magnitude 9, a gigantic one. And then an enormous tsunami that wiped out entire towns, and including the town of Fukushima. And yet, you know, the reactor was still standing. And there were backups, and when it lost grid power, there was battery power and diesel power, and those were made to last for a week. And it was thought that the grid would come up by then, but it didn't. And eventually there were problems, and a few workers were sent in and got a moderate dose, and one of them has since died of cancer. A lot of people died from nursing homes, people from intensive care units, from ERs were moved without drugs and oxygen. Neighboring towns would refuse to let these people in because they didn't want to catch the radioactivity, so they died of exposure, having to sleep outside in the winter. So the deaths came from the evacuation. There was only one death from the actual accident. And since then, there were changes to reactors so that neither power nor human intervention is required to shut down a reactor, that they'll shut down on their own, level passive safety. But if you ask people, how many people do you think died at Fukushima? The plurality of people say millions, or 100,000s or 10,000, thousands and things. And so no one picks one. And this is the rationale, in part, why people think it was so many, is because that's what news reports were saying. They were saying hundreds of thousands, millions will die, the same after Chernobyl. And it's because originally this was known as a linear no threshold model for radiation. In other words, that there's no such thing as a safe dose. And if you just take a high dose that's fatal and you extrapolate it down and figure out that, as the dose goes down, the cancers go down. If you have a dose that would kill, 1/1,000,000th of a lethal dose, you then say, okay, well, it'll kill 1 in a million people. And if you take 1 in a million people and you multiply that times the population, the 7 billion people on Earth, you end up with 7,000 deaths. And so those were the calculations that are calculating these gigantic numbers of deaths. It's taking very, very tiny doses and then multiplying that times the population on Earth. But since then, animal studies and looking at Fukushima and looking at Chernobyl and looking back at Hiroshima and Nagasaki and looking at Hanford nuclear power site in Washington and other places, and nuclear bomb testing, the data seems to suggest this threshold model, that as the doses go lower, and this is the part where your body's defenses does repair of DNA, that we can get to doses that are not linearly harmful, that there does seem to be such a thing as a safe dose. And then you no longer calculate up here millions of deaths, hundreds of thousands of deaths, and that this is where that giant difference. And this is also part of the problem with nuclear power policy in the US, is that it's based on this no threshold, no safe dose model. Where I went into, no, this is related to that. So it turns out that people that were evacuated from Chernobyl suffered more ill health than those that refused to evacuate and just stayed where they were. And if you calculate the change in life expectancy, if you just stayed near Chernobyl, you may have lost 2 months life expectancy from the radioactivity. But if you're moved to Kiev, you lost 9 months from fossil fuel pollution. And it's not just Kiev, but cities have a fossil fuel pollution cost in living in them. So anyway, just to give some perspective there. I forgot where it was. I was going to break for a question. Yeah, we'll talk about waste too. So what about waste? Well, I already showed you that coal gives you more radioactive, coal plant gives you more radioactive waste in the environment than a nuclear power plant. But solar and wind have their waste issues. But that said, because of the radioactivity, people are concerned about nuclear waste. And one thing you should know is that most of it decays within the first few decades, so about 30 years. And so generally nuclear fuel is just stored on site for about 30 years, and you let most of that radiation decay away. But some of it is very long-lived, and there's 3 approaches that countries take. They can bury it, you can recycle, reprocess it, or you just leave it on site and monitor it. And examples of that, Finland's an example of burial, and they've set up this extensive, right, there's a nuclear power plant right next to this extensive underground network still being built. But you pack away your excess fuel in these canisters, and they're sealed, and then they're put inside another canister, and then that's all buried, and then you cover it over, and then once you fill up a row, you close off that row. And so it's a stable area, and it's thought it could last indefinitely there, or long enough. And many countries take this approach and they bury it. The US, we set up Yucca Mountain to do that, and for political reasons that hasn't happened, but we do bury nuclear waste. There's a site in New Mexico. We don't talk about it because only the Navy is allowed to use it. So the Navy buries nuclear waste, but no one else is allowed to. But many countries take this approach, and well, I'll contrast that. It turns out there's natural reactors, and this is in Gabon. There's places where uranium has a concentration of U-235 that when it gets wet, because you need that water modulator, right, moderator to keep the reaction going. So when it rains, water gets into the site and nuclear reactions, and it becomes natural reactors until they heat up and they boil off the water and the reaction comes to a halt. And that cycle goes on, has gone on for millions of years. The uranium level is now low enough that the reactions have come to a halt, but the waste is still there. And people looked and said, well, how much has that moved? You know, what's happened with this buried waste? And nothing. You know, it's basically right where it's always been, and nothing's happened over millions of years. So there's that. Anyway, there's the French example. You know, a good part of the nuclear fuel is still unused after you go through the reaction, and you can reuse it. You can, there's breeder reactions, and you can go through several cycles and get a lot more use out of your fuel. And so significantly cuts down on waste. So you also end up using a lot less fuel. The problem is that uranium is very cheap. And so most countries just find it easier to just buy more uranium rather than reprocess what they have. And it's a complicated chemical process to do the reprocessing. And so most just say, oh, we'll use it and we'll bury it. But there are countries, I've listed them here, and the US actually does this in terms of our weapons. We reprocess the nuclear materials in those. But the French feel it's a more responsible. They say, well, higher cost, okay, but it's more responsible. You don't have to do any more. We can just use the uranium we have. We don't have to do any more, rely on any mining. We're generating less waste that's worth the cost. And as we saw, you know, French electricity is cheap. So there's that. But many people think what makes the most sense is what we do in the US, and that just keep it on site where you keep an eye on it. So, you know, the radiation is decreasing with time. You put it in canisters similar to the one being buried in Finland. And then you put those inside these big casks. You see people standing next to it. There's no radiation coming out of it. It's properly shielded. You can crash a plane into these. They're made the same as the bunkers for nuclear missiles. So they're considered pretty indestructible. And I think that's, yeah. So we'll end there. Back to questions.
So 3 people put in stack. This was pretty early in this section. So Alan Fierce was the first.
Hey, Alan.
Hi, Paul. Maybe I jumped in too quickly. I thought you were going to get into some of the advanced nuclear reactors.
But that's the next section. That's the next section.
All right, then I'm going to hold my question.
Okay. Okay.
So let's see.
Does it involve the Union of Concerned Scientists?
Yes, it
Okay.
does, actually.
Ah, okay. I had a feeling. Okay.
That's their new report?
Yeah.
Yeah.
So the next person was Tina Grosowski.
Hi, thank you. Thanks,
Tina.
Paul. Hi, Paul. Thanks for all of this. Mine was more a generalized question of perception, and wondered if youth today, younger people today, have a much different perception of nuclear energy than we all do as elders who grew up, with drills to hide under your desk, et cetera, et cetera.
Yeah, that's true. That's actually a good point. I didn't think about that, but now they hide from active shooters instead of imagining a nuclear bomb going off, right? Like we did. I don't
There's
know.
a lot of
actually.
young people involved in this field right now. In fact, it's kind of funny because we have a little gap that's starting to get backfilled now in terms of generations.
Yeah, actually, in terms of nuclear engineering, right, it is becoming a popular field again. You're right. There are young people that see this, and and just environmental issues in general have become very popular. And there are some that you're right that do see this as an answer. So you're right, David. I agree with you there. I don't know if you want to say more. Sorry, I jumped on you. Yeah.
Actually, Paul, can I jump in with a question about this last section?
Yeah.
It's troubling me a little bit. You pointed out how few people have died in these various nuclear accidents, and correctly you pointed out that there were 600 to 1,000 people who died in Fukushima during the evacuation. I'm not sure how many of you know about the fight that Massachusetts had with the building the Seabrook nuclear plant. I was actually part of the Attorney General's office team that was litigating the licensure of that plant by the Nuclear Regulatory Commission. But the case that Massachusetts brought was really about the off-site evacuation plan, which was inadequate. And my little piece of the case, or maybe not so little, was to prove that their evacuation plan for Hampton Beach and those beaches just to the east of the plant in the summertime, when the beaches were crowded, were going to kill thousands of people in the traffic jam that was going to result. People were going to be driving over lawns on the wrong side of the road. We had traffic engineers come in and testify to this. Anyway, I don't want to diminish the dangerousness of evacuations themselves. And we know that whatever happens in the future with nuclear plants, there will still be planning for what happens when there are releases of radiation. There have to be at least two options. There has to be an evacuation plan, and there has to be a sheltering in place plan. And it's dangerous if they are not sited in the proper location. And I think this is a real concern still about nuclear plants.
Well, it's why New York has shut down its Indian points, right? Out of that kind of concern. And there's actually another issue that is actually relevant, but I'm not really going to address it. And it's, trust, right? Do we trust the people, the companies that are building it? We trust that we're being told thing. And that hasn't always been there. And
do we trust the Nuclear Regulatory Commission?
Yeah. So that is an issue. That is an issue. Yeah. So the question is, can we learn to regain that trust, right? And that's that's sociology. I think it's not the science, which is what I'm concerned about here. In terms of, in retrospect, I mean, shelter in place was the right answer for Fukushima. In fact, they got more exposure by trying to evacuate than if they just stayed in place. And the main radioactivity that comes out initially is iodine, which your body absorbs iodine and goes to your thyroid, causes thyroid cancers, but there's two good things about that, actually. If you just take iodine pills, that'll block that. So it's easy to prevent. And actually, if you actually do get thyroid cancer, it's highly treatable. It really only kills people that don't get adequate treatment. So yes, there's potential for a lot of radiation. The majority of that radiation is the iodide, and it actually has a very short half-life of a few days. So after a week or two, it's gone. So it depends on how it's handled, right? And in Russia, they didn't handle it. They evacuated people. They got more exposure. There was a big spike in thyroid cancers, and not all those people got good treatment, and people were not given iodide and things like that. So you can, it's a complicated thing, but yeah. So I'll go with what you said and just add that piece to it.
Another piece of Chernobyl was tens of thousands of abortions, unnecessary abortions.
Yes.
And never been an effect, a correlation with any kind of birth defects.
Yes, that is true. That there was, because of all these warnings, particularly Greece and Denmark, I think were the two. Yes, there was a giant uptick in abortions. And yet when they've looked for actual birth defects or increases in miscarriages, that was never found. And so it was the fear, and same thing with the evacuations in general. It was the fear of radioactivity, and you're talking about traffic accidents, right? It's an excessive fear. Turns out to be more dangerous than the actual accidents themselves have been. And so this is part of, I'm not entirely trying to minimize that there's no risk, but that the risk needs to be seen in a rational way and not exaggerated, because an exaggerated sense of the risk itself becomes dangerous. Yeah.
There are a couple more questions that are actually along those lines. So it
Okay.
may be that you've kind of answered them, but one person says there's so much destruction because of Fukushima. It's hard to imagine that so few people died. Is there any data about how many lives were disrupted following the Fukushima disaster?
Oh, yeah, well, yes. So, I mean, tremendous numbers of people died from the tidal wave, right? But it was really, it just was not that much. The thing is that we can detect small amounts of radioactivity very well. And so there are all these graphics of these plumes of radioactivity coming out of Fukushima and spreading over Japan and going over the Pacific Ocean and wrapping around the Earth. But that's because we're really sophisticated at being able to detect small amounts, right? But if it's just a few percent over the background, you can detect it, but it's not really harmful. So there's that misperception about how much radioactivity was released, and actually ongoing. So there's this controversy now about all the water that has been used to cool it and is considered radioactive. There's 100,000 tons or something, some astounding number. And they wanted to dump it into the sea, and there was an uproar, and they were going to wait till after the Olympics to do it, right? But so I looked at the numbers, and it turns out if you took, so they took all that water, they ran it through ion exchange columns. So anyway, they were able to remove most of the radioactivity out of it. There's a few things, tritium and carbon-14, they couldn't remove, but they removed almost all the radioactivity. So like 1% or some small fraction was left behind, and that's what's going to be dumped. If they dumped all of that over the course of a year, it would be 1,000th of the background level, okay? But their plan is to dump it over 30 years. So we're talking minuscule amounts in terms, comparison to background, but because any amount of radioactivity is seen as awful, there's this giant uproar, and fishermen, don't dump this here, and this. Without looking at numbers, it's very easy to see this gigantic amount of water that's radioactive and it's being dumped, and how irresponsible Japan is. But when you actually look at the numbers, it seems like silly to be worrying about it.
So it's 5:13. I'm going to do one more question, and then I'm going to ask other people to wait until Paul's had a chance to finish the presentation. Okay. So Bern Kosicki has put in the back.
Yeah. Hi, Paul. I should say that up front, I'm sort of mildly on the side of going ahead with nuclear, but the big problem that I've seen, or that that the industry is really not cost competitive. That it's too expensive to build a reactor in the US these days. And,
Yes.
and the answer is not modular reactors. They're actually more expensive than a big reactor because, well, I think that the industry's been pitching these as being cheaper because they think they're going to be pre-certified off the shelf. And I'm not sure the NRC is buying into that. So,
yeah, there is that. Well, they're also hoping that they can make large numbers of them, right? That they have a standardized design and that the costs will come down just as anything else that's standardized, and you start making it in larger numbers, the cost comes down. But you're right. The reason that gigawatt reactors have been built is because you want to, it makes more sense financially to build a giant reactor, right? But I'll actually address that in a minute. I have a slide where I'll talk about with the cost issue.
And so Westinghouse is, and also the industry has been decimated as far as expertise. Westinghouse has been out of business now for 7 years, and everyone is taken off and are doing new things now. And so it's hard to see that, at least in the US, we can ramp up at the same kind of rate that you had on your chart earlier.
Yeah. Although, there was no expertise before that, right? That started from scratch. But you're right. But the one key point is the US. I mean, there's the rest of the world. And there's a whole developing world that is looking for energy, and its choice seems to be coal, gas, or nuclear. And so that's part of my goal here, is at least make people think that nuclear may not be an unreasonable choice there. And right now, China and Korea and Russia are the ones that are building those for those countries.
Well, so home Ontario. Look across the border.
Yeah, New Brunswick too. New Brunswick is going for the smaller ones. But yes, Ontario and New Brunswick have made a commitment. Yeah, so let me get back and talk about these small reactors. So these reactors are referred to in generations, and one was prototypes. Most reactors that exist today are generation 2, and those are the water-cooled steam ones that I talked about. After 75, they're known as Gen 3, and the more recent ones are known as 3+. And 3 and 3+ are substantial improvements. They're considered much more passive safety features and more efficient. They last longer. The designs are more standard. But they're still water cooled and steam generated. And they're designed, as I said earlier, that there's no need for power or any manual intervention to shut them down. So they're considered passively safe. And the problems of the accidents before are thought to be impossible. But then there's this new thing, Gen 4, the advanced reactors, and those are the smaller ones, SMR, small modular reactors, microreactors, experimenting with different fuels, different ways of packaging the fuels, different cooling systems, and do more advanced passive safety. So I'll look at a couple of those to give you a sense. So here we are, small modular, very small modular microreactors. And so they get as small as, so here's the reactor here. It's just a little bit bigger than a person. You don't need a containment building. They're air cooled. You can fit it on the back of a truck. The idea is you mass produce these. And so that's where the cost savings comes in, and that you can send these to remote areas. The Army is very interested in these. They like the idea of a reactor. You can just send it to a base and electrify your base, the next day, no matter where it is, remote places, and that you can just add these. You need more, so then you use 2 or 3 or 4. And they don't need water for siting, so you could really put them anywhere. There's a Danish company, I just saw this the other day, they're putting them on, they just started building this. They're going to put them on boats, and the idea is send these boats around the world to help electrify cities. And again, these same modular reactors. So Some examples is an Aurora one, air cooled. It's the fuel is put in it. It runs until it's done, 30 years or so. The reactor's underground. New Scale is building a small one in Idaho. This is what it's supposed to be looking like. There's a company called UltraSafe. It makes microreactors, again, underground. To give you a sense, it's the one happening in Canada. And I want to go a little more detail into this one. So the Department of Energy had a competition. The XE100 won it. X Energy is the company. It's a helium cooled, it's a pebble bed reactor. And so it's called triso fuel. So there's a fuel pellet, and this is smaller than a grain of rice, half a millimeter. So it's just barely bigger than a grain of salt. And then that's embedded in multiple layers. Some are spongy, some are super hard, ceramics, silicon carbide, some are heat proof. And so it's to protect against anything you can imagine. There's like a layer to protect it against that. And there's spongy ones, so it can take being smashed. And then these are about the size of BBs, and then they're packed together into like something closer to billiard ball size. And that's your pebble. And then the reactor, you just add your pebbles, and with time, they're removed from the bottom and you add fresh ones at the top. And so there's never a need to stop the reactor for refueling. You just keep adding. There's no worry about a meltdown. You can't get the fuel closer to each other. They're physically separated. These things are pretty much indestructible. And they're set up, if they heat up, they actually stop absorbing the neutrons. And so if it starts heating, the reaction stops itself. So it's one of the levels of passive safety. It's air cooled. If you lose electricity, it still cools just from convection. This is what's being built. It's being built in Idaho. They hope to have it done in 7 years. And the plan is to, if that works out, to start mass producing these for the Army and other things like that. So that's one thing of these pebble beds. There are various other things, different types of fuel. And the one I want to just talk a moment about is this is a molten salt one. And so the fuel is made into a salt, and it's dissolved, it's already a liquid, so you can't melt it down, it's already melted. There's no cooling liquids to worry about. It's just heat exchangers. If it heats up, it expands, and that slows the reaction down. So it also comes to a halt. And then there are these plugs. And so if it starts heating, it melts a plug and everything drains. And if it heats, and if that doesn't work, the bottom is made that it crumbles at an even higher temperature. And again, you go underground. And so it's also thought to be passively safe. They talked about the Union of Concerned Scientists. So they wrote a 120-page report that I had the pleasure of reading. And they're very skeptical of all these new designs, but their main point, and it wasn't really clear from executive summaries or any of the news coverage of it, their basic argument is they feel Generation 3+ reactors are really pretty good and safe and improving, and that time is short, and that we're chasing after these new designs, feeling that they're going to be the magic solution, and that they may solve one problem, but then they may bring up another problem. And so, like, for example, back to the pebble bed, they feel there's a proliferation risk here. That normally, you can't steal nuclear fuel because it's considered self-protective, because if you try to steal it, you die from the radiation. Or if it's sufficiently shielded, you're now talking something that weighs a couple of tons and you're just not able to move it. But they feel, well, yeah, but you can steal these pebbles. And so they're using that kind of an argument. But if you start doing the math and you realize, yeah, you need to steal 30,000 pebbles. And so to me, I'm not sure that was a reasonable kind of argument to come out against the pebble bed reactor, but that's the kind of arguments they were using. But I was actually surprised because it was their belief actually in Gen 3 plus reactors more than what I consider many picky assaults on the different Gen 4s once one reads the report. So the last thing I want to talk about is what's happened when plants have been closed. And Japan, they started building coal plants to replace the nuclear plants they shut down. Although this week, for the first time, they've reopened one of their nuclear plants. So they may be rethinking their decision. Germany, talked about, they've been getting rid of their nuclear plants and they've replaced it with electricity from Poland, which is coal-based. And so it's set them back. Massachusetts, we talked about when Pilgrim got shut, it set us back. New York has, because of the concerns like Alan mentioned, having plants near populated areas, has shut down the Indian Point plants, and they shut down 2 of them. This is after one of them. And what happened after it got shut down is renewables increased a tiny bit. Nuclear took a big hit and it was replaced with fossil fuels. And that's generally been the story, that when we've shut down nuclear power, it has not been renewables that have helped us, but it's been fossil fuels that have benefited. I guess the last thing here, what's stopping us from a big buildup? Well, fear, cost was mentioned, the politics, will, distrust, and just a general perfectionism, right? Don't let the perfect be the enemy of the good. And we're keep holding nuclear to a very high standard. Anyway, I just came across this. I mentioned the Reddit, and I saw this on Reddit today. And it shows several states actually have a significant amount of their production is nuclear. Illinois is the most, but there are 5 states that over half of their electrical production is nuclear. So it's not that the US can't do it. So yes, the last thing on coast, the issue of cost. So this is time going from 1950 to near present, and this is the cost. And initially, nuclear costs just came down very quickly, as you expect any new technology, as you make more and more. And these are color coded by country, and this dark blue is the US. And what happened in the US is it spiked up. But that didn't happen in other countries. France in the red has stayed pretty even. Japan has stayed even. Canada has stayed pretty even. Korea has stayed pretty even. So most countries have been able to keep nuclear costs down, not the US. And the reason is that we use this linear no threshold model still, that we still assume there's no such thing as a safe dose. And nuclear power plants are required to have as low as reasonably achievable doses. And so they're basically made to spend whatever it takes to lower the dose. And if a power plant can be made cheaper, then they're expected to throw more money into lowering radiation doses. So we're kind of stuck there. And the hope is maybe, this is one of the arguments for the Gen 4, the advanced, is that taking a fresh start, because it's not clear how we get out of this unless we really think how we regulate in the US. I mean, other countries are able to do it, but the US has gotten itself in a bind here. And my last slide, that basically I agree with Barrett. I mean, I approached this agnostically initially, but I think, yeah, we got to go with solar wind, but we got to be really careful not to shut down the nuclear plants we have, because it's been a mistake wherever that's happened. And I'm all for developing new tech. And I would also want to add that we're going to have to replace our fossil fuels quickly, and we're going to need some clean, dispatchable energy, and nuclear fits that bill. And there may be other ways of doing it, but right as I see it, nuclear looks like a prime candidate. And this last figure looks at our energy mix in New England over the past and the next couple of years, and nuclear has been heading down. Oil's gone down, coal's gone down, that's good. Hydro's gone down, renewables very slowly going up, and the big change has just been gas, and that's our challenge, right? What are we going to replacing the gas with? So on the subject of memes, I give you the Ford Nucleon. So thank you. So that was actually, we're actually considering that. That was actually a real thing. And there were actually nuclear planes were thought out, but the amount of shielding to protect the pilot was made it impractical. But yeah. So any further questions?
Yeah, what I'm going to suggest, thank you, Paul, is I'm going back to what I think will be a quick question. And then I know that it's 5:30 and there's an announcement. So I think I'll do the question, we'll have the announcement, and then if people want to stay and continue the discussion,
okay,
we can do that. So Maureen's asked, she said, you said that solar and wind were taking more space than nuclear, but was this calculation considering the space that nuclear waste takes?
Yeah, well, because of the high energy density, there isn't really much nuclear waste. And I believe if you take all the nuclear waste from all the reactors that was ever used and you spread it over a football field, I think it comes to like 10 feet high. I mean, there's just not a lot of nuclear waste. I mean, there's what they call secondary waste. So like these gallons of water at Fukushima, right? And things like that. So that can take space, but no, generally this is not, nuclear waste does just not take much space.
Yeah, that's an argument for nuclear, actually.
Yeah.
It's minuscule, and if we reprocessed, it would become even less.
Yeah, in fact, there's no need to ever mine any more uranium. We have enough, we could just reprocess it and we're good for hundreds of years. So yeah, that is one of the strongest arguments. The high energy density means besides reprocessing, we really don't have to fool with it much.
So Arnie, you said there was going to be an announcement. Is this a good time for that? Is Arnie here?
Yeah, I'm here.
Okay.
Yeah, I think if Tina's here, I thought she was going.
I'm here. Yes. We thought we'd just take advantage of having all of you here, and thank you, Paul, again so much. You obviously put a lot of thought and time into this presentation.
I will admit that.
Thank you. So we just wanted to get an assessment from the people who are here, from those of you who are here, excuse me, on a chapter meeting in in August, and whether people will be around and whether they would like to have a chapter meeting. We're considering having it, the topic be sustainable consumerism and, sustainable consumption, I'm sorry. Sustainable consumption. And I'll just read really briefly what we're meaning by that. Sustainable consumption is the use of material products, energy, and immaterial services in such a way that their use minimizes impacts on the environment so that human needs can be met not only in the present, but also future generations. So if we could just have a show of hands of people who think they'll be around in August for the chapter meeting, not deep dialogue. This is a deep dialogue, but the chapter meeting, which is on the second Tuesday of the month at noon. People interested would like to come to a chapter meeting.
Somebody was asking if it's going to be in person or Zoom. That would be on Zoom. Oh, no, I don't want to.
Okay, great. Looks like a fair amount of people. So that's really helpful. And you can be looking for the announcement about that later in the month. So thank you. So I guess if there's some people want to stay on and chat with Paul, are you open to that?
Oh, yeah.
I know some of us have to go. We still have more Zooms to go for the evening. But so Paul will let you and Amy take this back over. Thanks, everybody.
Thanks everyone for being here. So we had a stack from, I don't know who this is, but the email address is canopy.bart.
Okay.
If that person is still here. Maybe not. Let's see. I'm not seeing other questions. There's sort of conversation. So
Art is there and he's speaking. He's just on mute.
Oh, okay. I didn't see that. Bart, did you hear that? You're on mute.
Still on
Bart,
mute.
Bart, you're on mute.
Okay, how's that?
That's good.
There you go. You got you now.
So what, I already asked my question of Paul, so I'm done basically.
Oh, okay.
Thank you. We have a new stack from Dave Drayton.
Hi, and thanks for the fantastic talk. I really appreciate it. I learned a lot here. My question is basically, so I know that in China, there are a pretty good handful of new reactors that are in the works or getting planned right now. And so more than any other country by far.
Mm-hmm.
They would seem to not really have the taboo that we're dealing with here against nuclear. But I also know that they have a lot more oil, like coal, natural gas, like they have way more in that basket planned in the future.
Yes.
So I'm trying to figure out, for a country that doesn't have the taboo, why wouldn't they just go 100% nuclear? What are the downsides that they're considering that's holding them back?
I don't know. I mean, I know they're building both coal and nuclear at high rates, right? At I think a coal plant every week, and nuclear plants every several weeks. Yeah, I actually don't know why they're still. I mean, if you've been to China, you know it's the pollution issues are severe, and it's one of the reasons they are, you know, as green as they are, because they see how much they've suffered from terrible air quality and desert. The country's becoming increasingly desert too. I actually don't know why they haven't just fully gone, except maybe they're putting as much resources as they can into nuclear, and they still know they need a lot of electricity, and so they're using coal to fill up the slack. That's my best guess.
Probably a couple of things. That's
one other thing.
Oh, sorry.
No, just one other sentence. In terms of selling to the world, they're selling both nuclear and coal and gas. So it's not just in country; they're also with developing countries. Yeah, go ahead, Dave.
Well, yeah, I was on their for their own sake. It's probably strategic to see how well the nuclear build out works out, and it's much more expensive than coal. So that's the second thing. You can put a gigawatt of coal up a lot less expensively than a gigawatt of nuclear using conventional technology.
Mm-hmm.
Is that the case?
They're selling, as you say, they're selling it to the rest of the world.
Yeah.
I know that that's definitely the case in the United States, as we saw in that graph. It's super expensive to make nuclear.
Mm-hmm.
Was China on that graph? I don't think it was. But
No.
Do we have any idea of if it actually is more expensive to produce a gigawatt of electricity with nuclear in a country that doesn't have these crazy barriers that we have?
Well, you kind of alluded to it. Another thing, they're not just building standard nuclear plants, they're experimenting with these new types. So they're building pebble beds, they're trying these high temperature and fast reactors. So those are going to be expensive initially, right? If you're building these experimental ones, but they're also building generic at the same time. So it's not an answer to your question, but
okay,
that is a component of it.
It's worthwhile looking at France. One of the reasons they could build up in a decade was they used one design.
Yes.
That was a big cost effect.
Yes.
Apologies to everybody for taking more of than my share of the time.
Oh, please.
I've studied it too.
So
In fact, that's the hope with these small modular reactors, is to settle on one design and just mass produce those. Right.
Okay. Yeah, I mean, I ask the question because I know that in a lot of the outreach that our group does to the public through Facebook or whatever, one of the most common responses that I get in opposition to the work that we're doing is anything we do is just going to get blown away by all the emissions coming from China, because there's this statistic out there that they're producing a new coal or natural gas power plant every week. So what we do is just basically useless. And so I'm trying to figure out why are they doing that? So I guess I'll just keep doing some more research on that. But that makes sense.
If you look at per capita emissions, then we're the villain, not China. If you look at total, then China is the.
Oh yeah, I have a whole slew of rebuttals against that China comment. I'm just looking for more ammunition.
Yeah, well, at least they're trying. I mean, they're not, but yeah, they're also not trying by building the coal.
We should also keep in mind that we've mostly talked about electricity today, which is a fraction of the total need, and that the demands of the developing world are going to push the total need for energy will probably triple it. So reduction of use is not part of the picture at all. So that's another argument for nuclear, because it has a bigger chance of actually filling that need.
So we have a new question here. Is nuclear suitable for marine propulsion?
Well, the U.S. Navy thinks so, right? I mean, they've been running submarines. So in fact, small modular reactors have actually been around for quite a while. I mean, we've just been using them in submarines. Yeah, and as you know, it's been, people just don't think about it because there is this anti-nuclear base bias, and so just, I mean, this shipping is the big unknown in trying to electrify everything, right? I mean, there's this, batteries aren't going to work to get you across the Atlantic, so maybe people offering hydrogen or ammonia, things like that, but nuclear does seem to be a viable option. Especially if you're thinking long term, because which is what part of the reason the Navy was really went nuclear. If you're thinking long term and you just load up your fuel and then you're good for a couple of years, nuclear makes a lot of sense.
And some of the modern high temperature reactors can actually synthesize liquid fuels, which water cooled solid fuel reactors can't do at all. So that's another part of the picture: hydrogen and methane and ammonia and dimethyl ether and the rest of it.
There is one reason, I guess, that that people don't think it'll work for shipping, and that there are a lot of ports won't let nuclear ships into the port. So the fear, right, becomes a big issue.
We have another safety question. How much plutonium does it take to cause harm? How much plutonium is in that 10-foot high football-sized field?
It takes very little plutonium if you ingest it. Yeah, it doesn't take very much.
Well, actually,
but the thing is, how do you get it into you is part of the problem. And yeah, well, go ahead, Dave.
Well, if you eat it, it won't hurt you at all. It'll go right through you. You won't even absorb it. But if you get a powdered form in your lungs, then you're in trouble.
Oh, okay.
Because those alpha particles that Paul was showing us, your skin will stop them. But once you get them inside where they can kill 3 cells in their path, then you're in trouble.
Right. So this plutonium argument is used to scare people, because you can take the total amount of plutonium and you imagine dividing that up and spreading it over the whole earth, and everyone breathes in a little bit. You can kill hundreds of millions, if not billions, right? If you just somehow imagined how that was going to happen. But yeah. But one can imagine scary scenarios with anything, right? And I mean, the grid is very vulnerable and very vulnerable to cyber attacks. And the whole US grid could be shut down in ways that it may not recover for 6 months. And that's a frightening prospect to imagine no electricity in the country for a giant period, or a giant solar flare wipes out the US grid. I mean, if one has a good imagination, one can imagine all kinds of disastrous situations. So it's partly why I went by, nuclear's been around 70 years, and historically, there really have not been problems.
Truckloads of ammonia and and chlorine on our road are far more dangerous even than a dirty bomb.
Mm-hmm. Well, and then here we are in Boston, we have these giant gas tanks, right? And liquefied natural gas coming in and out of our port. Gigantic potential bombs that could, Alan is worried about evacuating near Seabrook, but what would happen if there was a giant gas explosion right in the Boston port? I mean, that would, so one can imagine things if that's what, and you can probably use terrorism to rule out anything, because you can always imagine some new kind of obscure event that a terrorist would do.
So we have a stack from Tom Amuro.
Oh, yes. Hi. I'm wondering what you think about fusion. I was on a call the other day with Laurie Trahan, and she's actually trying to fund some of the work that's being done by a company at Fort Devon.
Okay.
Commonwealth fusion.
Well, MIT is more positive about it than lately. So it's always been, 20 years off, right? Waiting for new technologies. But there actually has been some new technology lately, and that's the superconductors. That it does seem more plausible than it has in a long time. And something happened, was it yesterday? They reached a new temperature at some experimental reactor. So there was actually a positive step there. The giant one in France, the ITER, I believe it's called. I mean, that's not going to happen anytime soon. But there's a lot of companies that have formed with hoping that superconductors and other imaginative techniques, and they're getting lots of funding from Bill Gates. So, I mean, I wouldn't count on it, but I do feel more hopeful than last year and more hopeful than 5 years ago. So,
well, we'll ultimately crack that nut, but it's going to be a while after we do before we can roll it out. And fission we can roll out now.
Yeah.
So from
Is it any less dangerous? Would it help to alleviate the fear?
Yeah, we don't have the radiation problem. So, which is the big fear, right? And the association with nuclear weapons. So I guess a little fusion seems to associate, but it's, I guess you can think of it more as the sun, right? You think of it as a solar energy, packaged solar energy, and that might be more palatable.
Yeah, it's not quite radiation free. It's got a lot of high neutron flux, and it makes tritium, but it's much less than fission.
Yeah, there's not the long-lived actinides and
right.
Yeah, it's true. I wasn't thinking about the neutrons. Yeah.
We have a question from Marcia Hart. What do you think about the ASR problem at Seabrook?
So, this is with the concrete? Is that the issue? Actually, I don't know what the ASR problem is. I mean, I know there's been concerns with whether some of the concrete is failing. Is that what we're talking about?
Marcia, can you clarify?
Can you explain the question more? And I probably don't have an answer anyway.
It's a problem that occurs with concrete. It occurs in dams. It occurs in bridges.
Okay. Yeah.
Seabrook.
Yeah.
And it had occurred at Seabrook at the time that they very prematurely renewed their license.
Mm-hmm.
Then it went before the Atomic Safety Licensing Board, which are the ones who oversee the NRC. And it was a citizens group, the citizens within a 10-mile radius. And as I wrote earlier, I'm in Gloucester, so I am outside of the 10-mile radius, even though on a clear day I can see Seabrook from one of the beaches here. And we have an evacuation problem in Gloucester, no matter what sort of problem happens here. But one of the ones to be concerned about certainly is nuclear, because of the panic that would be caused by that.
Yeah.
So the concrete degrades, it's micro cracking. And I know it's the only plant in the country that supposedly has this. I've been an anti-nuclear activist for a very long time, but I have a great deal of respect for everybody in this organization, Mike Barrett and Jim Hansen, but I don't agree with you. And I'm really concerned about the circular economy and the idea of us stopping wasteful use and overuse of resources, which I feel the consumptive nature of our culture has really caused the pickle we're in. And I've almost accepted that closing any nuclear plants is a mistake because of the fossil fuel situation we're in and the lack of available renewables. But also I blame the nuclear industry for that lack of renewables. I blame the fossil fuel industry for the lack of those renewables and their unconscionable economic drive despite public health in many ways. And I don't think they took the subsidy money that could have gone to renewables. We were talking about that in the 70s at Seabrook. They could not have taken all the subsidies from the taxpayers they've had. And we don't ever include the problems that the waste causes in the cost of turning on your light bulb. So the light bulbs that have been turned on since the 70s, and I was arrested at Seabrook 9 times, and I'm not some foolish person who overreacts to silly things like the nuclear plant exploding. I'm concerned about the waste. I'm concerned about the waste we've created, the loss of some of it, the mishandling, the idea that we're now going to move it to Texas and New Mexico. And it's going to get there past where people live. And it's going to a temporary site. It's illegal to have a temporary nuclear site until you have a permanent site, but they're going to do it. I listened to the dialogues of the people in New Mexico and Texas. New Mexico is a minority majority state. So we've put, it's an EJ problem. We have put the most waste there of anywhere. And now we're going to put a whole bunch more of it there because it's a population who is considered to not be able to defend themselves as well as the people in Cambridge might. So when are we going to include the problems that we create in the cost of what we create so that people can actually evaluate the real cost of things?
Of course, that needs to apply to coal also and gas, right?
It needs to apply
the externalities. Well, the first part, I agree with you that this trust issue is a real issue. And the industry and the regulators need to demonstrate, that if nuclear is to go forward, that trust has to be reestablished. In terms of the cost of disposal, there's actually, that money is set aside in escrow. So nuclear power plants are required to set aside money for their decommissioning, for the disposal of their waste. And so that money has already been collected. And
not for the amount of time that the waste is around.
No. But the idea is that, well, what they're doing at the moment, I mean, Seabrook stores on site. For short term, they put it in a swimming pool.
They're unlikely to be stored. I think the cask storage on site is the safest thing that we have developed.
Yeah, and that's what they are doing.
That is not what they're talking about doing in New Mexico and Texas.
Right.
I just want to say we have a couple more questions that I want to.
Oh, yeah, okay. But I mean, I think some of your concerns are justified, some of them. But you have to remember, we're not talking about a whole lot of waste. And at least for the next 30, 50 years, storing on site is not a problem. And in fact, there's many things. I mean, it could well be that we'll want to just reprocess that fuel down the line, and it's better to have it accessible, or it'll be used for medical uses or something else that we don't know. We don't know what we're going to do in 30 years with it. And there's no problem with storing it for the next 30 years.
I do not believe in kicking that can down the road to my grandchildren.
Well, it's not that much waste. I mean, that's part of it. So it's not a giant thing.
It's not like salt.
I do want to give a couple other people a chance to ask their questions.
Okay.
I'll stop. Thanks.
Thanks. So from Julianne Carney, how much of an issue is the need for water in nuclear production? Water is an overused resource.
Yeah, well, that is, so the standard light water reactor, it is important, and that's why there are these giant cooling towers to cool the water down and before it's returned to the environment. But that's one of the advantages of these Gen 4, because many of them don't need water for cooling. In fact, most of them don't. And for many small modular reactors in general are helium cooled or air cooled or through other ways, just using the earth to cool it. So they're cooled in other ways. So the newer ones, it's not an issue. For the standard ones, it is an issue.
Well, what's being
or
done?
A limitation. Let me put it that. It's a limitation for the standard ones. It's not considered a limitation for the new ones.
What's being done with the water that's been used to cool the reactors? Where does it go?
So I believe, well, if it's, so some use a double cycle. So you have the water cools the reactor, it's under high pressure, and then it heats up a second bunch of water, and that second bunch then generates the turbines. And it's that second bunch that gets cooled and just returned. The first bunch I believe, just keeps recycling, and it does pick up some radioactivity.
Yeah, even the second bunch gets it's the water that cools that second bunch that gets taken out of the river and put back in the river.
Oh, okay.
And it's not that much heat, actually.
Mm-hmm. So the real answer is anything that's going to be radioactive just sort of stays on site and is continually used.
I think our last question will be from Dave Drayton. Dave, you both have a stack and you asked a question. Do you want to ask it?
Sure, since I'm unmuting to answer your question anyway.
Okay.
So just to be clear, so the cost of nuclear, which we've already established is super high in the United States, is it just super high in the United States because of the regulatory problems in our country? Or is there something else at play? The reason I ask is because I know that there's a plant down in Georgia right now that's currently in construction. They've gone from a $14 billion budget up to a $28 billion budget, and it's still not done. Mm-hmm. And it's years behind schedule. So I'm curious, what causes these huge overages, even when up front they know the regulations that are in place and can plan for that?
Well, the time actually is a factor. I mean, you need gigantic loans to build a nuclear power plant, and those you're paying back interest until the plant has been running for a while, to generate the money to pay off those loans. And so the more it's delayed, mean, those delays end up driving up costs. So there's that issue. And the other part, I think, is just the regulation, and that this idea that they can continually require more and more from the plant, because there's no limit to what's an acceptable dose. And so the standards can kind of keep changing.
Well, there's a couple of other things at play too, which is we haven't been building reactors for so long that we're still in the one of a kind mode. So if you start getting a standard design and deploying it, that'll lower the cost. And the other thing is peculiar to those Vogtle plants, which is that Westinghouse went bankrupt in the middle of this process. So that probably doubled the cost right there. And yet it's still going to be cost effective. It's going to make money.
Yeah, because that's because once it's built, it's pretty much built, and the fuel is not a significant expense. And so it's actually a very cheap way of making electricity once you have the plant. The problem is building the plant.
Okay, thanks.
It's time to close. So Paul, thank you so much.
Thank you all for the, and I'm glad I didn't get lynched.
Thanks, great presentation.
Yeah, and thank you for your expertise, David.
Right.